Hello everyone, I'm Aurora Rossi. I'm sorry that I couldn't attend the workshop in present, but I just got back from Japan just a few hours ago. And today I want to present you temporal graph neural network and their application. So just a few words about me. I'm a third year PhD student under the supervision of David Couder in the Coati team at IRIA Université Côte d'Azur. And in October, I will start a postdoc under the supervision of Petra Mutzel at the University of Bonn. And I decided to present to you this topic because I am a contributor of the open source package graph neural network. That is a Julia package that implements graph neural network. And in particular, I focused on the implementation of the temporal graph learning part. So the content of the presentation are, I will start with an introduction of neural network and recurrent neural network, and then I will move to the concept that it is at the base of the graph neural network, that is the message passing procedure. Then I will show you what is a graph neural network. Then I will move to temporal graph neural network and some real-world application, such as traffic prediction, brain activity prediction, and temporal cut centrality. So let's start with the definition of a feed-forward neural network. So it is a parametric function that is composed by multiple layers. And layer is defined as a fine transformation followed by a nonlinear activation function. And on the top image, you can see a layer of feed-forward neural network in which it takes as input some element of a vector. Each element is multiplied by a weight. Then there are summed together. And so this part corresponds to a matrix multiplication. And then we add a bias vector, and at the end it is performed an activation function. If we can concatenate several layers, we obtain a multi-layer perceptron. Another neural network architecture is the recurrent neural network. This model is similar to the previous one, but it also maintains a memory of past input. And these kind of architecture are suitable for tasks in which we have time series data, such as natural language processing and speech recognition. And as you can see from this formula, we have that x of t is the input, so our time series at time t, and then we keep an hidden state that is taken from the previous time step. Two popular ones that are a bit more complicated than this formula are the gated recurrent unit and the long short-term memory recurrent neural network. Now that we have defined some preliminary introduction on machine learning, let's recall what is a graph. So a graph is a data structure where we have a set of nodes V and a set of edges E. And when we use graph in machine learning, we can have other information attached to them, and so we can have additional information to at the level of nodes, at the level of edges, and at the level of the whole graph. And so these are additional information that we can assign to node, edges, and the whole graph. Now we move on to the concept of message passing. So the message passing procedure is at the base of a graph neural network and is composed by three main steps. So let's see them from the point of view of node 3 for simplicity. So the first step is the computation of a message of the neighbor of node 3. So we have two neighbors, and we will compute two messages that are computed with a function that takes as input the additional information, so the feature of the node and its neighbor. And then the second step is the aggregation. And to aggregate, to combine these messages, we use a permutation invariant function, such as the sum or the average. And the last step is the update. So we want to update the current information of node 3 using the aggregated message. And to do so, we use function gamma that takes as input the current information of the node and the computed message. And so we will have an updated information. The message passing procedure is done in parallel for every node. And here I show you just the point of view of node 3 for simplicity. So now we are ready to understand what is a graph neural network. And in fact, a graph neural network applies the message passing procedure to a graph, and in particular use as phi and gamma functions, so the function that compute the messages and update the current information. It uses they are implemented as a neural network, a feed-forward neural network. And so now we pass to the concept of training. So a graph neural network has to be trained in order to perform well, because at the beginning we have some random weights that are the weight of the neural network, and we want to optimize them. So the training is an optimization problem in which the model output has to minimize an objective function that is called loss function. And to do that, we need a dataset called training set that use the that is a dataset in which we have the ground truth, so the target we want to achieve, and we compare with the loss function the model output and the ground truth. And in this way, we can update the model weight using the gradient descent algorithm. So now we move on, and we will understand what task can GNN perform. There are several tasks, but the three main tasks are graph classification, link prediction, and node classification. And the classification depends on how we treat the resulting feature, the updated information, after the message passing procedure. And for example, so when we look at the graph classification problem, so it's the problem of determining the category of a graph. For example, in the case of in chemistry, we want to understand the kind of molecule that is the graph. And so after some layer of message passing, we can combine all the information, and using, for example, a sum. This operation is also called pooling, because it reduces the dimension of our data, and we will obtain what is called a graph embedding. So the representation of the graph as an array. And with that, we input it to a multi-layer perceptron that will output the class of the graph. Similarly, the node classification, so it's the problem of determining the category of a node. And in the case of a molecule, it's the decision of what kind of atom is a node. And so also in this case, after performing some message passing layer, we use so we want to understand what is the node 6, and we use its feature as the input of multi-layer perceptron, and again we will obtain the class. For the link prediction, so it's the problem of determining whether or not there will be an edge between two nodes. So again, after have performed the message passing procedure, we take, for example, the feature of node 3 and 6, and we will input them into a multi-layer perceptron, and we will obtain the answer yes or no. Now I will show you the two most popular graph neural network layers. So the first one is the graph convolutional neural network, and the second one is the graph isomorphic network. The second one is more expressive than the first one, and is strong as the Westphalian-Lehmann test. And it is inspired by the CNN, which is a model for images. So now we move to temporal graph. So in machine learning, we use just two definitions of temporal graph. So the first one is called static temporal graph, because the topology of the graph is fixed, but the node and edge feature change over time. And the second one is the dynamic temporal graph, in which the structure of the graph change over time, and usually in application the number of nodes is always the same, and the feature also of node and edges change over time. So depending on the kind of temporal graph we are working with, there are different kind of temporal GNN. When we use a static temporal graph, the temporal graph neural network are called spatio-temporal GNN, because they are composed by two parts. The first part is graph neural network on the fixed topology of the graph to model the spatial dependence, and then it is combined with a recurrent neural network that we defined before to model the temporal dependence of the feature. Instead, if we work with dynamic temporal graph, we can use temporal GNN, and there are several ways to design a temporal GNN, but the simplest one are when we applied a graph neural network to each snapshot of the graph, and then we combine the embedding of each snapshot together. Or more complicated one, for example, the evolve GCN, use a recurrent neural network to evolve the weights, so the learnable parameters of each graph neural network over time with a recurrent neural network. So now we move on to real-world application. So the first example I want to show you is the traffic prediction problem. So the traffic forecasting is the problem of predicting future traffic trend on a road network given some historical data. And in this example, we will use the METRLA dataset, and I will show you the model taken from the paper Diffusion Convolutional Recurrent Neural Network Data-Driven Traffic Forecasting by Li et al. So the METRLA dataset is composed, it contains the traffic data from 207 sensors in the Agway of Los Angeles County, and the graph node are the sensor, and the edge weight are the distance between the sensor, and the node feature are the traffic speed and the time of the day collected from March to June 2012. So the model is called DCRN, and it is a spatial temporal model because it uses a diffusion convolutional layer to model the spatial dependence, and the gated recurrent unit to model the temporal dependence. And so the model takes as input the static graph and the temporal feature that are given in batched. So, for example, 3 time step, and then the prediction are the values shifted by 1 time step that are then compared with a loss function with the targets for the training. And here are the results. So we can see that for different times and different metric, the DCRN is the most performant technique. And the metric are the mean absolute error, the root mean square error, and the mean absolute percentage error. And now I want to show you the plot in which there are illustrated the ground truth, the output of the spatial temporal graph neural network, and the output of a recurrent neural network. And we can see that the temporal graph neural network model generates smooth prediction, and it can predict the start and the end of the peak hours. Because in this plot we can see on the x-axis the 1 day, and on the y-axis the velocity, the speed of the cars. Okay. And the next example is the brain activity prediction. In the paper of forecasting brain activity based on model of spatio-temporal brain dynamics, a comparison of graph neural network architecture, the authors used the same model that was designed for the traffic forecasting problem, and they apply it to the data of resting state functional MRI. So they are data that contains the brain activity of humans that are contained in the Human Connectome project. And in this case, the graph is constructed in this way. So the graph nodes are representing the brain region, in particular 180 regions, and the edge weight are the number of fibers connecting to brain regions. So in this case, we have that the graph is it contains the spatial information of the brain, and instead the node feature are the time series that represent the brain activity of the region. And also in this case, the accuracy is the mean absolute error, and it's quite low. And here there are 3 plots of 3 different brain areas, and in which we have that in light green there is the truth, and in the darker green there is the output of the spatial temporal model. And in these 2 heat map, it's a way to represent the brain activity across time of all the brain regions. And you can see that the ground truth and the model, the 2 matrices are very similar. The next example is the temporal cut centrality. So first I want to define the temporal cut centrality, starting by define a temporal graph in another way. So it's a graph so a temporal graph is a graph in which we have a set of nodes, a set of temporal edges, and a set of time steps. And a temporal edge can be defined with the U, V, which are the two nodes that are connected at time t. And a temporal walk from two nodes, from node U0 and UN, is a ordered series of node and temporal edges that is represented by x by zeta, and it has to follow the temporality. And the temporal centrality, so it's the sum, a weighted sum of temporal walks that start from different node and end in node U. And in this formula, n is the number of temporal edges in the walk zeta, and T1 is the time step at the start of the walk. And in this case, to predict the cut centrality, the model is quite complicated with respect to the one that I showed you before. But to simplify it, at each time step of the graph, a subset of neighbor is sampled for every node V, and they prioritize the node with a higher out degree, and then the messages of the neighbor are combined using an attention-based weighted aggregation, and after that the output are given to a multi-layer perceptron that converts these embeddings into the CATS-inspired ranking score. And these are the results. So the performance evaluation is done with the top n%. The dataset they used is quite big, and also it takes graph of with lot of nodes, and then we see on the left the plot in which they compare their method velocity and the algorithm for exact CATS centrality computation. And these are the results in which they compare their model with another temporal graph neural network model, and they perform better. And the KT is the Kendall-Tau correlation. Thank you very much for listening and for the invitation.
Aurora, do we have any questions? Do you have any questions online also, maybe? So I was wondering, for example, in your model for the transportation, basically you are getting a lot of data for your prediction. I was wondering, do you know if your model, for example, is robust, if there is some data loss, or can you even try to see how to minimize the data you need to still have good predictions?
I want to first say that I just implemented the model, but I'm not an author of the paper. And usually in machine learning, more data you have and more the prediction have good quality. And in the paper, they don't discuss the fact to have a small number of data, but they try to use as much data as possible to improve their accuracy.
I see. Thank you.
Thank you.